Colocar en tela cheia.
¿Puedes ver mi pantalla?
Sí, está perfecto. Bien, estimados participantes, es una alegría presentarles al profesor Edson Sampaio de la Universidad Federal do Ceará. Al inicio empecé a hablar con Edson en español porque Edson ha pasado una pasantía en España, entonces siempre cuando nos encontramos, entonces tratamos ahí de entendernos en español, ¿ya? Así que tengan la confianza de poder preguntarle a Edson durante su charla en español. ¿Está bien, Edson?
Está bien. Creo que no voy a hablar español porque creo que no estoy preparado de hablar de matemáticas, o sea, pero si me preguntan, seguro que voy a contestar en español también, pues, en portuñol, ¿no? Porque al final no tengo tan buen español, pero sí.
Muy bien, Edson, muchas gracias. Y bien, comentarles un poco que Edson trabaja, ¿no? Usa topología para estudiar singularidades. Aquí en Brasil justamente existe un enorme grupo de esta línea donde usan, tratan de estudiar singularidades. En particular, Edson es uno de los investigadores acá en Brasil, en particular un amigo que trabaja en esta línea. Y les deseo pues un máximo provecho, ¿no? Y cualquier duda tengan por favor la confianza de preguntar a Edson, ya sea por el chat o activando su micrófono, ¿ya? Y agradecerte, Edson, por esta oportunidad de platicarnos un poco sobre tu trabajo. ¿Ya? Tienes 50 minutos para tu charla ahí, pica pantalla y puedes iniciar, por favor. Muchas gracias, Edson.
Muchas gracias también. Muchas gracias por invitarme a participar de este increíble evento. Voy a cambiar para inglés porque no estoy preparado, creo que para hablar de matemáticas aún. Entonces, I will talk about global bi-Lipschitz classification of semi-algebraic surfaces. I want to say some words before start the talk. In fact, I thought to talk about some algebraic metric topology that I developed with some collaborators, but was hard to. I thought a lot about that, but it was hard to talk in only 50 minutes about that subject. So I choose to talk about a recent result of mine and my collaborator about classification of surfaces. Let me say that the results presented in this talk are in the preprint titled Global bi-Lipschitz Classification of Semi-Algebraic Surfaces, written with Alexandre Fernandes. You can find this preprint in my ResearchGate webpage and also in my homepage. If you type my name in ResearchGate, you can find it. Okay, you can find also my other preprints and articles. In general, I update my homepage and my ResearchGate. You can find all my papers there. So let me say some words about the introduction and the motivation on this work. Firstly, in this talk, we consider semi-algebraic surfaces S in Rn. And some semi-algebraic here means some set which is given by inequalities and equalities of polynomials with real polynomials, okay? And surface means outside of the singular set, this is a smooth manifold with dimension 2, for example. Okay? So when we consider connected semialgebraic surfaces, we can put there two distance, canonical distance. The first one is the inner distance given by the length of arcs connecting 2 points living on S. Okay, and in fact, the second one would be the restriction of the Euclidean distance to S. But in this work, I will consider mainly the inner distance given in this way. Okay, and we are planning to classify all the surfaces up to bi-Lipschitz homomorphisms with respect to the inner distance. I will call here this kind of bi-Lipschitz homomorphism by inner lipomorphism. So just an example, for example, if you consider Nash surfaces, it means that smooth surface which are semi-algebraic and complete, they are closed set in Rn, for example. We present a list of symbols, theta S, which represent the orientability of S, GS of which is the genus of S, and some number ES and some numbers beta 1 up to beta S, which are rational numbers associated to the ends of S. I will explain what means that. And these numbers, these symbols, will determine S up to inner lipomorphisms. So let me remind the topological and smooth classification of surfaces. For example, if you have two surfaces, connected surfaces without boundary, which are smooth and compact, the following statements are equivalent. They are homeomorphic, they are diffeomorphic, and because the inner lipomorphism is an equivalence between topological and diffeomorphic equivalence. Of course, if the third item here is equivalent also to the other ones, and you know, in fact, we have only two invariants to classify smooth compact surface, which are the orientability and the genus. Here, theta x is equal to 1 if x is orientable, and -1 if it's not orientable. Okay, and g of s of x is the genus of x. And of course, we also have a classification when we have boundary. Now, when we consider boundary, we have to add a third invariant, which is the number of components of boundary components. Okay, but we have also the all these items are equivalent, homomorphic, diffeomorphic, inner lipomorphic, and has the same invariants here, like orientability, genus, and number of boundary components. But now, if you consider surfaces which are not compact, or which has, or a surface which has a singularity, okay? The problem of classification is hard. Let me show some examples to clarify what I'm saying. For example, if you consider X to be R2 and Y to be this cylinder and Z to be the paraboloid, for example, X and Y are orientable, has the same genus, but they are not homeomorphic, and of course are not diffeomorphic. And also, if you consider R2 and the paraboloid, they are diffeomorphic, but they are not inellipomorphic, for example. In the non-compact case, diffeomorphism does not imply inellipomorphism, which is the case in the compact setting. Okay. A second example, if you consider compact sets, but with singularities, for example, if X is the sphere and Y is the horn, the cutted horn with some disk, the union of these two guys, and they are homeomorph, but they are not inellipomorph, and they are of course compact sets, but they are compact manifolds, topological manifolds, but not the smooth manifolds, because Y has singularities. So we are planning now to consider any semi-algebraic surface, of course, closed semi-algebraic surface, and it can be non-compact, and also it can have singularities also. Okay, so there is a result, a very important result proved by Levi-Brahe. It gave a topological in a bi-Lipschitz classification for germs or in the local case. He proved that if you have a germ or semi-algebraic set, in fact, a surface here is a semi-algebraic set with dimension 2. Okay. Let's say X at a point A with isolated singularity and connect link. So there is a unique rational number beta greater than 1 or equal than 1, such that the germ X is in a bi-Lipschitz homeomorph to the germ of the beta horn given by in this way. In fact, this gives a classification of surfaces in the local setting for germs of surface. Because if you have a surface, semi-algebraic surface with isolated singularity, we have the link is the link of such surface, which is the link means here the intersection with a small sphere with center at A, example. This is a smooth and compact surface, so each component is diffeomorph to a sphere, for example. So if you take each component if you remove the point A, we have a surface in exactly in this setting of the theorem. So if you now take any surface, we have some invariant, some number beta for each component of the link. And this number, this collection of numbers will give a classification in the local case. And now we are planning to present a classification in the global set, in the global case, okay? So let me define some invariants, which will be important to understand our invariant. Okay, let me consider X with a semi-algebraic surface with isolated singularity. And for each singularity, here, I'm considering singularities in a Lipschitz singularity. That means around P, the surface is not a bi-Lipschitz, in a bi-Lipschitz homeomorph to a disk, for example. So we consider this number, which is the, as I said before, this is the number of connect components of the link at P. And now you can use local structure theorem, conical structure theorem, or in the global structure theorem to find some large radius r, so that when we intersect x to the ball of radius r and remove the balls centered at the singularities with radius 1 over r, this will be a topological surface with boundary, and the topological type of this x prime does not depend of the big R, for example. You can find it. And then we define the orientability of x to be the orientability of x prime, as we can see in the slide. So we define the genus of x to be the genus of x prime, and of course, which is the genus of x. And for each p, there is some small r, so that the intersection of x with the ball is the union of some surfaces, and which surface xi is a topological surface. And by the theorem of bi-Lipschitz, there is some beta I, which is the Horn exponent of xi, given by the theorem of bi-Lipschitz. That means xi is inelipomorph to the beta I horn. And then by reordering the indices, if necessary, it may assume, for example, beta 1 is less than beta 2, etc., up to beta of the number of connect components of the link. And in this way, we define this invariant. The beta of x is just this vector, this point in the space with that dimension, okay? Some Lx upla. And we have also a kind of bi-Lipschitz theorem in the infinite case. That means when we take an end of x, let me say E, and here end means a connect component of x outside of that ball of radius r given by in the definition of the in the last slide. So for some end E, there is a unique rational number between 0 and 1, such that E is inelipomorph to a beta cube, given by in this way. And also you can prove, for example, this tube, the inner-Lipschitz type of this tube does not depend on A, for example. So with that theorem, we can define other invariant, which is, let me say, E of x is the number of ends of x, like here. Let me say A1 up to E1 up to EEx. Okay, and for each end EI, there is some beta I, which is the exponent given by the above theorem. And we can also, as before, assume that beta 1 is less than beta 2 up to beta E. And in this way, we define this invariant. Beta x of infinity is just the beta i's given by this way, okay? So we have the invariants, the orientability, the genus, the local exponents given in the last slide, even here, no? The local exponents, beta x of p, and the exponent at infinity given in this way. So the theorem is, we define the following invariant given by in this way. We consider the I'm going to consider only the case when we remove the singular set. This is we call the regular part of X. That means that that regular part of X are all the points on X, such that around that point, X is innerly homomorphic to a disk. Okay, so we only consider the case when this guy is a connect set. In fact, we can define our theorem works in the non-connect set also, but the proof is a little bit hard, and the invariant is also a little bit hard to define. So I'm going to consider only this case in this talk. Okay. So we consider the collection given by the orientability, the genus, the exponents at infinity, and the collection of exponents in the singularities. Okay, the singularities. And we call this collection the inner Lipschitz code of X. And we denote it by code of X, like here. Okay, this is what I said. So let me present some inner Lipschitz codes of some now very well-known surface. For example, the right cylinder is orientable, has genus 0, has 2 ends, and the exponents of each end is 0, and there is no singularity, so we put empty here. And the unbounded Mobius band, also this case is not oriented, has genus 0, only one hand with the exponent is 1, and there is no singularity also, so empty as well. And the global horn is, as I defined before, is given by the theorem of bi-Lipschitz. So is oriented, genus 0, only one end with exponent 1, and has one singularity with exponent beta, for example. So we have this cubic surface, which is oriented, has genus 1, 3 ends, because we have 3 lines at the tangent cone at infinity, because I'm assuming the A and B are different of 0, and A is different of B. And there is no singularity, so empty here also. The paraboloid, which is orientable, genus 0, the exponent at infinity has only one end, and the exponent is 1/2, and there's no singularities. And the last one, I think it's not the last one, it's not the last one. The torus is oriented, genus 1, compact, so there's no end, so empty here. There's no singularity, so empty here. And the Klein bottle, that which is not oriented, genus 1 is compact, so there's no end, so empty here. And there's no singularity, so empty here also. So maybe you can, with that example, you can more or less has some feeling of the invariant. And in fact, our theorem is the following. 2 surfaces, X and Y, which are semi-algebraic and with isolated singularities, are innerly homomorphic if and only if their inner Lipschitz code are equal. I will give some ideas of how to prove it, or how to prove it. In fact, the main part of this theorem is to prove that that theorem. That means a hint of x is given by is enantiomorph to some beta cube, and because that when you write the x has the local part of around the singularities, and when you look at infinity, you have ends, and you have the part outside of the ends and outside of the neighborhoods of the singularities. This is a topological surface with singularities, with boundary. And there we have a classification. So in fact, you can, since we are considering inner Lipschitz singularities, we can find if you have the same genus and the same orientability and the same number of boundary components, we can find a inner lipomorphism between two surfaces with the same those same invariants, and we can find also in bi-Lipschitz homomorphism between the ends and between the local part, and there is some work to do that in a Lipschitz way, but that are not so hard to prove. That this is the main tool of the theorem. So let me give some hint how to prove it, and I will present some applications of that classification. Okay. So first of all, we take some pancake decomposition of E. These pancake decomposition are the following. You can write E has a union of some sets Xi, and that sets Xi has some good properties, and among them, the main one is when you look the inner distance given by the length as before, and the outer distance given by the restriction of the Euclidean distance, we can they are equivalent. Xi has inner and outer distance equivalence. Okay, so we can always write E, a semialgebraic set has a union, finite union of has a, let me say, Lipschitz normal embedded sets. Lipschitz normal embedded sets are just the sets which has inner distance and outer distance equivalent inner and outer distances. Okay, we can call these also quasi-convex sets, as is in the title of the paper. We gave that decomposition. It's a paper from Udika and Parusinska. Here is the reference. Okay, so we can always take this one, and then let me just give a definition. A semialgebraic set is called a beta strip if that set is innerly homomorph to some strip like that. It's just some kind of for some A. We can prove also the inner Lipschitz of S beta does not depend on A also. So with that definition, we can prove, for example, for each I, Xi is there is some beta I such that Xi is a beta I strip. There is for each I, Xi is innerly homomorph to some S beta I for some beta. Okay, and then other thing that I prove is if you have two strips, two beta strips, such that the intersection is only one arc. They share in the intersection only one arc going to infinity. and the union. So then the union is a beta strip where beta is the maximum of beta I, which is the beta of xi, and beta j, which is the beta of xj. We can prove that. So if you have two strips, the union of that strips, if they share only one, the intersection is only one arc, this is still a beta strip where beta is given by this way. And in the end, to finish this, so if you have now, for example, E is by the cylinder structure, global cylinder structure, we can prove, for example, E is a cylinder. So we are going up to the end, and in the last step, we have, for example, two beta I strips, such that the union is some topological cylinder, and the intersection are two arcs, because we glue up to the end because we have only finite xi's. So we in some moment we find only two xi's like that. So in the end, we can prove, for example, the union of such two yi and yj, such that the union is a topological cylinder. This is a beta 2, where beta is the maximum of beta I and beta j. So this is more or less the way how to prove that some end is inelipomorph to some beta tube. But I said that there is a unique beta tube. So if there would be some other ones, let me say beta tilde, that if E is a beta tilde tube and also a beta tube, we have to prove beta and beta tilde are equal. But we can prove, for example, in a canonical beta tube like P beta is ln E. That means the inner distance on it is comparable with the outer distance. So if X is inner Lipschitz to some P beta and also inner Lipschitz to some P beta tilde, we have then P beta tilde is inner bi-Lipschitz to P beta. But because P beta is inner Lipschitz, is ln E, in fact, we obtain outer bi-Lipschitz homomorphism. That means a bi-Lipschitz homomorphism with respect to the outer distance. And then is a task to prove, in that case, if you have two sub beta, some tubes bi-Lipschitz homomorph with respect to the outer distance, the betas are equal. So this is more or less the way how to prove the uniqueness of the beta in the theorem. And then let me say some. I would write some pictures here, how more or less how that would be the picture of the proof, but I forgot my digital board. I cannot do that. I'm sorry. So some applications. In fact, for some cases, we can even present a normal form of the classifications, For example, for Nash surfaces, the following statements are equivalent. They are innerly pleomorph, even if they have the same orientation, the same genus, and the same exponents at infinity. That means we have a bijection the number of ends are equal, and we have a bijection between the exponents. And then, in fact, as I said, in this case, we can even present a normal classification. We can exhibit elements on the class of the classifications. For instance, take theta between -1 and 1, and G some natural number. So there is some n theta G in some Rn, which is a compact Nash surface, such that the orientation of that surface is theta, and the genus of that surface is G. You take one, or you prefer. If you are in the case of the oriented case, it's just some B-torus, some torus, some sum of torus. Okay? Then for a positive integer number E and some beta rational in QE, there is some type here, some in QE, so that we have beta 1 less than beta 2 up to beta E. We can remove E distinct points in that surface, n of theta G. Let's say x1 up to xe. And we can define f in such a way, just given by this formula. And we denote the image of f by the Nash surface. We can prove, for example, this is a diffeomorphism. So this is a Nash surface. And also when we have the compact case, we just denote this guy to be the original end. Okay. So if you take the image of f to be the image of f is denoted by this way, we have the following theorem. Let's see what I wrote here. Yeah. So if n is a Nash surface, so we have orientation of it, genus of it, and some exponents at infinity. So what we can prove is the surface given by the above process is innerly promorph to n. So because the uniqueness given by the last theorem here, right? Because if they are equal, we have a lipomorphism between n1 and n2. We can find, in fact, normal forms to n, right? To that classification. For it, n, we can find in this process one which is innerly promorph, exactly one, which is innerly promorph to n. A second application on it is a classification on properly embedded minimal surfaces with finite total curvature. They, in general, are not semi-algebraic, but if you read the proof, we can reproduce the same proof if you know how are the ends of a surface. And it follows from a result of Burago that the surfaces, the minimal surfaces with finite total curvature has exponent equal to 1. So there's no information about exponents at infinity. So the unique information about the exponents, the unique information at infinity are the number of ends. And in fact, Burago proved each end of a such surface is innerly promorphic to some R2 removed some ball, for example. So we can read our proof and find the following theorem. M1 and M2 are innerly homomorph if and only if they are the same genus and the same number of ends. Because I'm considering surface in R3, which are properly embedded, so they are always properly embedded surface in hypersurface are always orientable. So M1 and M2 are orientable in this case. So they have the same orientation. So the last one that I want to present is classification for complex algebraic curves. If C1 and C2 are semi-algebraic curves, and if you denote X1 up to XR to be the irreducible components of C1 and Y1, YS to be the irreducible components to C2, then the following statements are equivalent. C1 and C2 are homeomorph if and only if they are innerly homomorph. So in the case of curves, the topological classification is the same of the inner bi-Lipschitz classification. And if and only if for each singularity, they have the same number of irreducible components, and there is some bijection between the singularities, the inner singularities, so that they have the same genus, each irreducible component has the same genus, and the same number of ends, and the same number of connect components in the link of X, of at P, for example, of course, with that bijection. And then if you have these, we can show, for example, they have the same inner Lipschitz code, so we can prove they are in homomorph. Of course, if they are in homomorph, they are homeomorph. And it's easy to prove, for example, I did not say about that. I just said how to build, if you have the same Lipschitz code, how to construct some inner homomorphism. But of course, if you have an inner homomorphism between two surfaces, they have the same inner Lipschitz code. I did not say, sorry for that. But that's all. Thank you very much. And gracias por su atención.
Muy bien, Edson, muchas gracias. ¿Algún participante que desea tal vez hacer una pregunta, alguna duda, inquietud para Edson? Bien, Edson. Bueno, en realidad acaban de compartir la lista de asistencia, tal vez están un poco ocupados ahí. Quería preguntarte, tal vez algo general, particular.
¿Vale?
¿Existe alguna forma, algún computacional de calcular aquellos códigos que ustedes encuentran, sobre todo los betas, esos códigos que aparecen ahí?
Eso no hemos hecho esto, pero sí que habíamos nos preguntado de que sería una pregunta guay, o sea, no sabemos cómo, o sea, talvez un código que tú pones creo que mejor que esto es, tú pones aquellos invariantes y tú puedes encontrar una superficie que tiene aquellos invariantes. O sea, si tú encuentras un algoritmo de como este, creo que estaría demasiado guay. Creo que sería una óptima tesis de doctorado, creo.
Okay.
Pero sí que no sabemos cómo. Sí, esta es una buena pregunta.
Y igual también, porque ustedes generalizaron el teorema de bi-Lipschitz, ¿cómo que se llamaba?
bi-Lipschitz. vibra ahí.
Ajá. También en la versión de él también, no, alguien en la literatura no.
No, creo que
En
no.
ese sentido. Ah, ya.
No. Pero sí
Ya.
que en el caso de él es bastante sencillo porque,
Ujú.
como he dicho, no hay topología. O sea, si tú tienes, como es local, la topología, todo es lo mismo. Entonces, si o sea, tú puedes elegir, tú tienes formas normales. Eso es. O sea,
Ujú.
en el caso
Ah,
local, tú tienes formas normales.
ujú.
Tú dame un invariante, o sea, el número de exponentes. O sea, tú tienes una superficie que, tú quieres una superficie que tengas como el link, tengas el con componentes conexas y que tenga, cada componente tenga un exponente beta i. Entonces tú puedes
Ujú.
presentar una que tiene justo aquí, o sea, porque tú tú pegas várias cornetas, o sea, várias cornetas aí e se pode dizer em espanhol, cornetas também, horn,
Sí,
no sé, cuernos, vale, vale,
Ujú.
cuernos.
Ujú.
Pones vários cuernos, o sea, vários cuernos, tú tienes que tal vez aumentar la dimensión, pero sí que tú puedes exhibir una superficie que tienes justo aquella invariante. El problema es que
Ya.
cuando tú, por ejemplo, no tenemos, o sea, hemos presentado una manera de encontrar formas normales para superficies de Nash. Pero si tú, porque no hay singularidades. O sea, las superficies son más o menos sencillas. Pero si tú permites que tenga singularidades, creo que va a quedar un lío. O sea, tiene que ser realmente un buen algoritmo, creo. Porque
Ujú.
no, o sea, tú puedes, tal vez, con solo una singularidad, tú ya puedes, o sea, ya sé más o menos cómo construir una cosa de eso. Tal vez sí, o sea, pero creo que tiene que ser una persona que tiene tiempo, o sea, como he dicho, tal vez una tesis de doctorado, porque tienes que trabajar un montón, ver cómo hacer algunos casos, de caso con una singularidad, con dos, y tal vez aparezca uma coisa assim que, o sea, el algoritmo tiene que ser así, creo.
Ah, ok, perfecto. Muito obrigado. ¿Existe alguien que desea tal vez? Aún todavía tenemos un minuto.
Sí, profesor, sí, doctor, me permite una
Sí,
curiosidad.
sí, adelante, adelante.
Buenos días, le saluda el profesor Dolores Sánchez
¿No?
de Lambayeque, Chiclayo. Eh, la curiosidad es, generalmente nosotros asociamos la función de Lipschitz a reemplazar digamos, en los teoremas de existencia y unicidad de la continuidad. Mi pregunta, curiosidad es, la función de Lipschitz que el profesor pone en su exposición es la misma, la que conocemos, o es otra función de Lipschitz, y si es la misma, ¿cuál es la importancia de esa función en la superficie de Nash? Muchas gracias.
Vale. Mira, aquí en la realidad no es la misma Lipschitz porque cuando tú trabajas ahí con Lipschitz, es Lipschitz con respecto a la distancia euclidiana. O sea, tú miras las funciones que son Lipschitz con respecto a la distancia euclidiana. Pero aquí estoy hablando de Lipschitz, o sea, que son Lipschitz con respecto a la distancia interna, como es definido ahí, como, déjame mirar si está aquí, aquí en el principio, como aquí, ¿no? O sea, la distancia aquí no es la norma de x menos x1 menos x2. En general, eso puede ser más grande, general, ¿vale? Pero hay, o sea, entonces, en general, Lipschitz con respecto a esto puede ser que no tenga unicidad de soluciones, cosas como esas. Claro que hay existencia por el teorema de Peano, porque son, sí que si es Lipschitz con respecto a esta distancia es continua, por ejemplo. Pero aquí hay una cosa que que tal vez no había dicho, es que Lipschitz, con respecto a esa distancia, estoy interesado, o sea, la importancia, por ejemplo, en superficie de Nash, es que quiero saber cuáles son las superficies que puedo andar por geodésicas, porque los homeomorfismos bi-Lipschitz con respecto a la distancia interna controlan geodésicas. O sea, si tú tienes una geodésica que tiene longitud L, si tú aplicas por una aplicación Lipschitz, Lipschitz, la longitud de esta hora es una cosa acotada por una constante que ya está definida en principio. O sea, la constante que daba la definición de bi-Lipschitz. O sea, que tú puedes, una aplicación en bi-Lipschitz es que, o sea, Lipschitz, por ejemplo, es que no tengo, talvez voy a intentar escribir con touch, no sé si voy a poner, que es que la distancia de la función f mal, ¿no? Es mal, pero vamos a ver. Muy mal, ¿no? No sé si voy. No voy a poder escribir. No, perdón, pero no voy a poder escribir, creo. Pero es que la distancia de f de x hasta f de y, por ejemplo, es acotado por una constante veces la distancia de x hasta y, por ejemplo. Y aquí la distancia es esta, o sea, dada por... Entonces, para contestar rápidamente, es que la importancia es que con esta definición, con la clasificación, puedo decir cómo puedo, cuáles son las modificaciones que puedo hacer entre una superficie a la otra sin caminar mucho. O sea, con una acotación en las geodésicas que son importantes en geometría diferencial, en EDO y todo eso, ¿no? ¿Comprendes? Que, o sea, la importancia en general es porque para esto puedo controlar las geodésicas. Hago cambios que... No sé si
Okay.
ha podido comprender
Sí, está
alguna cosa de
bien.
eso.
Entiendo la distancia de entre superficies. Ok. Thank you. Anderson.
Ok, muchas gracias. Muito bem, Edson, muitíssimo obrigado. Agradecerte nuevamente por la maravillosa palestra que has brindado. Vamos a presentar. Puedes ya dejar de compartir su tela. Vamos a presentar aí o certificado virtual que vamos a mandar via e-mail depois. Tá? Como agradecimento a sua participação como palestrante. Muito obrigado, Edson.
Eu que agradeço. Muchas gracias. Hasta luego.
Chao, chao. Muy bien, estimados participantes, vamos a ir alistando el siguiente expositor, Nicolás. ¿Logras escucharnos? Adelante, Nicolás, ¿puedes escucharnos?